You won't want to be referring to them constantly when you're solving problems, but it will be useful to be able to check and make sure that you're not making a mistake to write these rules down on the back of your page. So as you know, the test for this module does not require you to know the rules for the biconditional, but the quiz does. You won't be tested on them, so in order to do well on this test, you'll only need to have memorized the rules for the conditional, the conjunction, the disjunction, and for negation, elimination. Okay, so once again, this is not meant to be any kind of a shortcut. I'm just going to be highlighting the main points, assuming you've been through everything. First thing to remember is that the book actually requires you to identify the rule you're using on each step, and we do not. So if you'd like to do that, if you'd like to follow the book, that is fine. It's perfectly okay to do that. It can get a little bit messy, but in the way I'll do it here is the way I'll be expecting you to do it on the test. So what you'll be doing twice is you'll be given an argument, and you will be required to assess its validity. So you'll have an argument that's represented as a sequent like this with the turnstile, which identifies the conclusion. Very often at this point, I will be using the convention that allows us to drop the outermost parentheses, and it's okay for you to do that too. So when you're given an argument like this, the first thing you have to do is to write it down in the proper way. So you're going to have to rewrite all of these. Don't just use the existing typed argument as part of your proof. So you line everything up vertically like this. The premises come first and the conclusion is written at the end. Now, the absolutely most common mistake the first time through is to forget to negate the conclusion. So remember that anytime we're testing for validity, we're essentially employing the method that we use in for the shortcut method in truth tables. Is we're assuming that the premises are true and the conclusion is false and trying to generate a contradiction. So in the context of refutation trees, assuming the conclusion is false means negating the conclusion. Now, the second most common mistake is to incorrectly negate the conclusion. So, as I said, I am using the convention now of dropping the outermost parentheses. That's dangerous. It's common, it's normal. We're going to do it pretty much until the end of class. At least it's going to be permissible. But it's dangerous for people who have not learned to recognize woofs and main operators. So when I negate this conclusion, I cannot simply put a negation here. Why is that? Well, what have I negated? I've negated the t. I have not negated the entire formula. How am I going to negate the entire formula? Well, I have to rewrite that original formula as a woof. Okay? So that is the most common, well, the first most common mistake is simply to forget to negate the conclusion. The second most common mistake is to negate it incorrectly. So negating correctly means being very attentive to whether or not you're looking at a woof or something that is just in accord with the convention of dropping the outermost parentheses. All right, so negate the conclusion properly. The second most common mistake is forgetting about the very advisable, though not absolutely necessary, rule of doing the non-branching formulas first. So I really suggest that you take this as an absolute. Do the non-branching formulas first. So in order to know that, of course, you need to know the rules for decomposing these formulas, and I'm not going to review those rules here, but assume that you know them. But if you choose not to follow this rule, then what very often happens is you get a very complicated tree. And the more complicated the tree is, the more likely you're just going to make a silly mistake. All right, so we have 4 formulas. The first 3 are conditionals, which are branching, but then we have a negated conditional, which is non-branching, so we'll do that first. So you know that the rule for the conditional is it's not the case that if A then B goes to A and not B. So here T is A and B is, it's not the case that not T or not S, so we put another negation on the outside of that T. So T and not T or not S, and we dispatch. We look for contradictions. There are none. We look for new formulas that we created that are non-branching formulas, and it turns out we have that right away because we can now just apply the double negation rule. So we have not T or not S by double negation. Now we immediately dispatch that formula. And now we have left 3 conditionals and a disjunction. And both of those are, of course, all of those are governed by branching rules. So at this point, we're free to choose any one we want, but sometimes it's smart to choose one that looks like it will generate a contradiction. And it's pretty clear that that's what we've got here. We have not T or not S, so if we decompose that, we're going to get an immediate contradiction with this existing T. So we go to not T or not S, dispatch the formula, check for contradictions immediately, and we see not T contradicts T. There is no contradiction between the not S and anything above it. That's a T. And, that is an X, Okay, so that closes that branch. And now the remaining formulas will only be decomposed somewhere under the not S. So what do we want to do? Well, it turns out that both the if M then S and the if R then S will generate contradictions with the not S. So you can choose either one of these to do. Okay, so I've decomposed if M then S. So I will check that. And now I have not M or S. I look for contradictions. Not M, there is no contradiction, but S, there is an immediate contradiction. So I will close that with an X. And now again, there's only one branch open. Now it's not a terribly common mistake, but one possible mistake is to look for contradictions in the wrong places. So if I had not found a contradiction here, I might have been tempted to go hunting for it by descending another branch, but that is not possible. All you do is keep going up. You only look for contradictions up the branch. Remember, each of these branches is a line on the truth table. Okay, so now let's just go ahead and do if R then S. Okay, so not R or S, dispatch, and we will just go ahead and make a note here. Always dispatch formulas immediately after decomposing them. And once again, we have S contradicting not S. And the only live branch is not R. Okay, I'm going to finish this a little bit unconventionally so that you can see what happens if we don't notice a contradiction and also other things that are important. So let's just suppose that we had not noticed that S contradicts not S. Is that a giant mistake? Well, the answer is no. It's a little unfortunate, but it's not going to ruin your refutation tree. So let's spread these out a little bit, because if we fail to notice a contradiction, or alternatively, if there just isn't one, then we have multiple live branches. And with multiple live branches, what you need to do is you need to decompose any remaining formulas under both of them. So again, I'm perfectly aware that S contradicts not S, and we should just be closing this off, but let's not. Let's just see what happens if we don't. So we have one more formula, if T then M and R. And what I'm going to do is I'm going to decompose this formula down below, but now, since I have two live lines, I need to decompose it under both the not R and the S. Okay, so I've decomposed if T then M and R as not T or M and R twice. I now dispatch this, and I'm working under both of these now. Now, of course, I can now see, right, that not T contradicts T. M and R does not contradict anything, but over here, again, not T contradicts T, and M and R does not contradict anything. So I've closed these two out. Notice what I've done is in both cases, I've traveled up. I've never traveled down. I've only traveled up the branch to reach a contradiction. Now, suppose I get to this point, and these are still live. These still have not been dispatched, so there's more work to do. But suppose I get to this point and I say, oh crap, I could have closed this right here, S and not S, but I didn't. Now, of course, you could just go back and erase everything, but suppose I just want to close it now. Can I do it here? Well, the answer is yes, because the rule says that if there's a contradiction anywhere along the branch, then you can close it. So you can actually just go ahead and close this right now. Even though it is not a contradiction with M and R, it's a contradiction still between S and not S. So the point here is nothing terrible happens if you don't notice a contradiction immediately, as long as you notice it eventually. Now over here on this M and R, there is no contradiction yet. You might smell one because you see a not M and you see a not R, but there is no contradiction yet. But you can find a contradiction very quickly by simply decomposing M and R, which is going to be our... All right, so we've dispatched M and R here. And now we see that M contradicts not M. Also, R contradicts not R. That's not important that there are two contradictions. One contradiction is all we need. Two contradictions adds nothing. So we close this. And now we're completely done with this proof. Notice that I did not need to decompose M and R over here. That's okay. It's okay that that was never decomposed. There's not a rule that says you need to decompose every decomposable formula. If a contradiction occurs, then we're done with that particular branch. Okay, so what can we conclude from this? Well, every single branch closes, So this is valid, as you know. If there had been a single open branch anywhere, then it would be invalid. So it's very important to make sure that you explain what makes it valid and what makes it invalid precisely. Precisely explain why it is valid or invalid. So the proper explanation of validity is just valid because all branches close. How could things have turned out different? Well, suppose the original premise had been, if not T, then M and R. What would that have looked like? Well, we could actually just go back and change that. If not T, then M and R. Not T, then M and R. Now, we'd never operated on that until we got right down to here. So how would that have been dispatched? Well, it would have been not T or M and R. Not T or M and R, right? And then there is no contradiction between not T and T. In fact, they mean the same thing. And we would have had a little bit more work here to do, actually. We would have had to decompose these two double negated T's. And so we would have had to write T here and T here, dispatching each. And then we would have said, okay, there's nothing more we can do here, but there is no contradiction. And so if that were the case, and now there is absolutely nothing more to do, this is a fully decomposed tree. In that case, we would say invalid because there is at least one open branch on a fully decomposed tree. It's okay if you just say because there is at least one open branch, but remember that can only be the right answer if that branch has been fully decomposed, if there's nothing more to do under that branch. Okay, so negate the conclusion properly, do the non-branching formulas first, always dispatch formulas immediately after decomposing them, and precisely explain why it is valid or invalid. And really, if you've been watching this and you're kind of getting it, but kind of not, it's almost certainly because you just have not committed the rules to memory, and that is absolutely essential before you make any attempt to take this test. All right.